discharges, and based on the velocity, force, and all those things, we could find a relation for viscosity. So we can actually do it experimentally with that. That was one way of doing it, and that was not really practical because we don't have that long plate that we can drag in. So there are some variation. They call it cavity way to do that. So they make a small cavity, and there is a roller on top of that you do that one. So, but it's still not accurate going to a practical limit. The distance between that plate and the surface cannot be adjusted. So basically, we went to another way of doing it over ramp. So you put a block, a lubricated rod over ramp, and then you try to adjust the angle of ramp so that it slides down with a constant velocity. Then from the equation we obtained, we could find mu viscosity. But that wasn't really very practical, again, because then you have that variable height or the thickness or the adjustment. In this case, call it T. We used to call it T. The thickness of the lubricated fluid between the plug and the ramp was not adjustable precisely. So that method is also not accurate, right? But this method is in fact very accurate. In fact, if you go one of our labs in the lab downstairs, they use this precisely exactly the same thing to measure the viscosity, right? Now, we developed a relation for that in the last class, but look, we ignored the bottom, right? Ignored that. So we only considered the fluid between the cylinder and the outer cylinder, which is rotating. I should show that with this, with omega, with a constant velocity. Omega. So we only consider the fluid between on the surface of the cylinder and the outer cylinder so that is rotating with omega. But we ignored the contact between the fluid and the bottom of this outer cylinder. So it's not contact, it's just that small distance T that they come together, close together. And between them there is a fluid. So this blue is your fluid with viscosity. This blue is just your fluid with viscosity of mu that we're trying to measure. Now, one question for you is, how can we incorporate this effect of the bottom in contact with the cylinder? How can we add that to the effect of course, the surface of cylinder has major effect because it's bigger than the contact surface between bottom and the cylinder. But we know that there is some fluid there, so our expression we derived in the last class is not really precise. How can we incorporate that? So in other words, I want to convert that to this problem. So right here, we have a rotating disc. Let's say we have a rotating disc with the speed of omega. So this disc is rotating with omega. And there is another disc that is fixed. It's not rotating. It's fixed, but it's connected to a transducer, so we can measure. So this is fixed to the wall, but there is a transducer, so you can measure the torque. So this torque M, you can measure it. You can have that. But the bottom disc is rotating, and there is a fluid here between them, right? There is a fluid sandwich between these two. Now, for this problem, I want to find the relation between M function of mu. What is that relation? If you go back to this problem, on the surface of cylinder, we had the same velocity. You see the velocity was velocity at this point. So if this rotates, the outer cylinder, the red one, is rotating. At this point, we have a velocity vector like that. You see that? All the outer cylinder, and the velocity was simply the outer diameter times omega, or 0 omega, right? That's exactly what we had in the last class. And it was same, and it was same everywhere. We could take it out of integral, and we could end up with a simple, very simple equation. That's that. But look at here. Every fluid here in contact, look at this disk. Any element here you pick, when you rotate, you have a velocity vector here. V. So if you can see this is the center, that velocity vector depends on the radius. This is R, is going to be R omega. It's not R0 or R0 times omega. So it's variable. So in fact, if I want to draw it here, every element here, this is the center, this is one element, this is another element. Just try to be like 3D view of the elements here. See that? When it rotates, every element, they get a tangential velocity. If it rotates this way, they're going to get a velocity which depends on the distance from the center here, R, times omega, the velocity of this. The velocity of this is the same, right? But the distance will change. Now, can you find a relation between mu and torque? And
yes.
How do you do that?
Well, it's pretty similar, isn't it? Except for the only thing. The only thing that's different is the velocity is dependent on the
radius
from the center.
The radius. So going back to the previous class, the equation we had this equation. Tau was for the dF, the force was tau dA, right? For every one of these elements, the infinitesimal force dF that comes from the friction between fluid and surface is going to be tau dA. This equation is valid for anything because it's in differential form. It's infinitesimal, right? So for tau, what should I write for tau? dF is equal to, we assume that it's Newtonian. What was the equation for Newtonian fluid? Tau was mu du dy. Right? You have to figure out what's the mu, what's the d, u, and y. So look at the distance gap between that. If you look at the gap between here, the velocity at this bottom is v, right? The velocity at top is what?
0.
0. So in fact, you write for this delta u, the change in the velocity is what? V minus 0. That's the change in the velocity. What's the change in the y? The thickness of the fluid enclosed between these different surfaces. What was the thickness? T. So this is also T, right? So in fact, if you go back to your note, you get mu v over t, and you say, well, this is still the same, just like the previous class. But what is my velocity here? What should I put for velocity?
R times W.
R times omega, right? So you say dF is equal to tau dA, which tau is what? Mu v over t times dA is equal to, what should I put for v? R omega. It's not R0 omega, it's a variable R. It depends on the distance from the center. You studied polar coordinate before, right? Cylindrical coordinate. Is there anybody here that never had cylindrical coordinate before? So here you say mu, instead of v, you put R omega over t dA. So if I integrate all these forces, what do I get? Resultant force. You remember vector statics. F resultant is summation of forces. And if I integrate all the little moments generated by this guy, I get what? The resultant torque, which is equal to what? M, resultant torque. See? That's what my sensor is measuring, the resultant torque. So what is the moment coming from one element? The moment dm is what? R distance times df, right? So if I use that, here I can write dm is equal to R times df. What was my df? Mu R omega over T dA. And if I integrate all these little elements, all of the elements, over the entire area, what do I get? The moment of all those little elements combined together, what do I get? The resultant moment that is applied to the top plate, which is equal to the moment read by the sensor. Guys, this is the probably easiest problem in this class. If you have trouble understanding this, you really need to study, please. Last year, I got an email from the Department of Mechanical Engineering that can you come and do some problem solving for students because they make bad grades, they have difficulty. And I think the reason for that is because you really need to put a lot of time on this. Really need to put a lot of time on this. Multiple vector statics by 10. Multiple vector statics by 10, factor of 10. That's the time you need to put in this course. Because this is the easiest problem in this course, unfortunately. We are going to get really, really hard soon, and we are going to fly. And the test exams are not going to be easy. I don't simplify things. If you're a mechanical engineer, are really graded really accurately. For civil engineer, this course is okay. I mean, you have to pass it, that's it. But for mechanical engineer, this course is a dedication. Right? So, these classes, the beginning of semester, that's fine, but please study, please try hard. You know that the homework, I post the homework, right? The solution to those homework, you can get it online. I know that, you know that, right? Don't do that. Solve it yourself. And if you do that, you realize every problem takes like half a day if you want to solve it yourself and get the right result. Okay? But we still have time to recover. If you really don't understand that, all you need to do, go back, read the double integration, calculus, double integrals. You need to review basic calculus and you're fine, you'll be fine. Eventually you will start understanding. Did you review double integration calculus? Did I put the link to review videos? You need to do that as soon as possible. All right? So if I add this a small tiny moment generated by this just friction of just one element on the surface of the disk, if I add all this dm, what do I get? The resultant moment. That's what my sensor is reading. My transducer is reading. Right? So all I need to do is to evaluate this integral. Now I want to make a meter opportunity. Is there anyone that wants to come to evaluate the integral over the surface of this disk? You want to do that? Look, you can't just like the previous example, you can't take all this guy out and just say multiply that by the surface of this, which is pi r squared. You can't do that. Why? Because r, the radius is on the integral. The radius depends on the location r. Right? The radius is not constant. In the previous example, we just solved on the surface of cylinder, so the radius was constant. You are not marching all over the disk. The reason that I'm solving this because this is a tiny itsy bitsy problem compared to your homework, the last one. The last problem, you have a cone. You have a cone, right? And this cone is inside another cavity, right? And then he rotates the cone, and there is a fluid between them, between cone and the surface of cavity. And you have to develop the relation to find relation between the viscosity of fluid mu and torque. And that's way more complicated than that, but you need to understand it. So is there anybody who wants to do that? And you may not like this because this is called parametric modeling. So we have all parameters mu, a, but soon we get a lot of numerical examples. Just wait. We'll do a lot of numerical examples. Is there anyone who wants to do that? This integral, all you need to do, you need to expand this integral. And you know, this is the double integral. It's over the area. You have two integrals. Sometimes they show you with one integral, say area, or double integral, and no text. So the double integral, I want to do double integral over this cylindrical disk. You see? That's a cylindrical disk. What coordinate system should I choose? Do you remember calculus is you use either Cartesian xy double integral or cylindrical or spherical. We did a lot of things in calculus, right? Which Cartesian system is suitable for this problem?
Cylindrical.
Cylindrical. That means instead of integrating, this was the basic Cartesian xy, dx, dy, and this was your integrand, right? Instead of doing that, this problem is easier to do rather than that. You do r theta, right? But how can you do that? Well, if you go back to the double integration principle, you realize all you need to do, this was dA in Cartesian form, right? dA was dx dy. What was dA in cylindrical? Do you remember that?
Would it be dr d theta?
Getting close.
dr divided dz.
No, that's if you want to go
Oh,
and see.
okay.
You just do it in, like, you see the bottom of this plate.
R dr d theta, R squared dr d theta.
Yeah.
R dr d theta.
Let's see what it is. Let's say this is your cylinder. This is your circuit, right? And you have an element here, right? Let's say this is your element. Okay? And from here to here, let's say it's R. And let's say this angle is d theta. D theta. Right? Now, this is square. I want to zoom it here. I want to zoom it here. Zoom on this square. Like that. You got 4 sides. This side, from here to here, is in the radial direction. So if from here to here is R, what's from here to here? dr, right? Do I get that? It's just a change in the radius. So from here to here is what? dr. And what's the value of this side, the arc?
D theta?
You see, you have a circle, and the radius is r. And you have theta here. What's the value of this arc? Guys?
The length of the arc?
Yeah, if this is arc theta, what's the length of this arc?
Oh, wait. Is it omega?
We don't have omega here. This is theta, and this is radius. Arc. And I want to find the length of this arc.
Sine theta?
Is it R times theta?
R times theta.
Theta over 360 times 2 pi r.
It's just this length, right? This length S from here to here is just arc theta. You never had this before?
Oh, yeah.
If you don't never had this before, you are in a big trouble. I can tell you that. You are in a huge trouble. Now, the way I do that in the previous courses, vector-static, mechanics of materials, structure analysis, all of it has something to show a student to memorize, like the way you tackle it. But this course you cannot memorize. This course you have to really understand what's going on. You have to really prove it yourself, otherwise you fail. I give you the equation, I give you all the numbers, but you don't know what number to substitute in what equation, because you have to really know what's going on. So in a circle like that, we had before, the arc length is r theta. So what's the arc length here? What's this side? What's your reference side?
R theta.
Yeah, but what's my theta?
D.
D theta. So it's going to be r d theta. So what's the area of this square? dA, the small area of that is what?
R d theta dr.
Yeah, this side by this side. This side is dr times r d theta. This we can memorize that. But when you assemble all in the fluid mechanical problem solving, you have to really understand it. So using this relation, I put it back here. Instead of dA, I write what? R dr d theta. That's my dA. So I'm going to expand that. I'm going to expand this relation. So you're going to get what? Double integral r mu r omega over t. Instead of dA, you just write r dr d theta. Now you tell me, we have double integral r theta. R goes from where to where? R goes from? Look at this. What's the value of the radius at the center?
0.
0. So R goes from 0 to
R.
to some R, which if I look at the problem here, the outer radius of this was what? Ri. This is the bottom disk, right? Ri. Ri. The outer radius of the outer cylinder was Ro, right? Ro. So I can P, because I'm just doing this relation for the bottom cylinder is moving, I can P Ro. But you can't precisely say, is it going to be Ri or Ro if they are very close to each other, right? But what we are writing here, the cylinder that is rotating is the Ro. So that's the reason that I use Ro. So it's going to be R from 0 to Ro. And theta from where to where? Theta is from
0 to 2 pi.
0 to 2 pi. 0 to 2 pi. Now, I want to give you a quiz level opportunity. Simplify this relation. Simplify. Yeah, you should put on whiteboard. If you want to do that. Yeah, that one's right. Yep. First, he brought all the constants out of the integral. You see those constants, omega, mu, r, omega, mu, and t, the thickness, they are not depending on the r or theta, the parameter of integral. So he brought it out, and then he got R1, 2, 3, RQ, dr, d theta. Now go ahead and next step. Yeah.
Can you explain again why you used the outer radius and not
The outer radius, yes. Because I use this here, the velocity here, if you write it like that, the velocity here is r omega. and this goes anywhere. So in fact, the velocity here is 0, right? The velocity here is 0, the velocity is on omega. So in fact, you're integrating on the outer disk. You're integrating on the outer disk. So that's the reason you go from 0 to outer. But there's going to be, if you want to do it more precisely, you should say RO plus RI divided by Q. Because you assume the cutoff is between the outer diameter and inner diameter, because you go to the surface of cylinder. So that problem is also that posed. So the way you can do that, say average RO plus RI. But I didn't do that, I just did this. Because that makes the equation to be very long. Okay.
Right direction, so 69, 4, 5.
Oh, okay.
No, not a single. Pay attention. Which one is theta? Which one is R? So this is R from 0 to R0. This is theta from 0 to 2 pi. Pay attention to that.
Quick. Okay, I needed the well, I'm going to do the integral here, so.
Yeah, separated. You see, you remember back again to calculus, we had we call it integral that you can separate. So if R and theta were not like depending together, you could separate them, like R times theta or R sine theta times R. You could say now integral R times integral whatever theta. So this problem is a perfect example of problem you can separate them. So let me write it for you. So here you did, this is right, omega mu over t. Do this for R, first write theta, 0 to 2 pi d theta. This is integral over theta times integral over R from 0 to R0. R4, yeah. Now go ahead and finish it. You already did that.
So I just
Yeah,
did R.
you just did that.
Yeah.
So what do you get for that?
Is
What do you get for that?
2 pi.
2 pi. So the end result is what? The end result is, this is going to be 2 pi. This is going to be what exactly we wrote. So R, this is, I'm sorry, this was R3. So you get R4 over 4, and then just 0. So R0, 4 over 4. Now let's assemble all together. So your left-hand side is M. So I'm going to write the equation here. Your left-hand side was M is equal to, thank you. Your right-hand side is, so that's your M, left-hand side of the double integral. Your right-hand side is omega mu over T. Omega mu over T. That coefficient times 2 pi times R0 over 4. Now solve that for mu, and you get the equation. Mu is equal to mt divided by 2 pi omega R, and this 4 also goes to pi. For disk. Now that means if you can read the torque from the sensor, you have the value of the thickness, right? You have the value of the angular velocity, you have everything, everything you have all the value in the lab. All you need to do to set the torque in your machine, set the velocity, angular velocity in your machine, and then read the torque. The rest of dimensions are here. And then it gives you this velocity. All right, before I leave chapter 1, because there are some important information that is not covered in your book for chapter 1. I want to show you some videos and we go over the definition of a streamline, the straight lines and path lines, steady flow, unsteady flow, laminar flow, turbulent flow. So it's a bunch of definition. I want to quickly over them and then we go to chapter 2.
Can I ask you a question really quick?
Yeah.
Where'd you get the dm equals rdf? I didn't see where you got that from.
That comes from electrostatics. So basically, where did I put? So you remember in electrostatics we had this relation. Moment is equal to R cross F.
Okay.
Right?
Yes.
So if you consider this is the actual big moment is equal to the distance times big force. So if the force is infinitesimal, dF, what do you get? R cross dF is what? dm, infinitesimal moment. And because the force and moment are exactly perpendicular, you see, when you rotate this disc, the force here, the friction force, the touch force is in this plane, the torque is in this plane. You see that? They are 90 degrees perpendicular. So instead of cross product, I write RDF, dm. So it was extremely easy. Instead of 3D vector cross product, I just did it because they were perpendicular and the moment is just in the z direction. And that's going to be the one that sensor is reading. Not just for flat plate work. The surface we did it last class. Now if I want to do the entire equipment, what should I do? Add this contribution, do that at home. And then you get a longer expression. This needs to like something that it's kind of like obstacle against the fluid flow. The fluid is going to go around it, okay? And then you have, we call it field, velocity field. You see, at every point, fluid has both y velocity and x velocity. And so you get velocity is a vector. So it's going to develop a field, and if you actually can visualize this or observe this in the actual life, it's a little bit harder compared to computer simulation. You can find this velocity field. Now, in this velocity field, I want to write the expression here. The definition of velocity is what? dx. So v velocity, what do we write here? So the fluid velocity, if we consider 3D, so the x component call it v, u, and then I mean you can write it like this. You can write it 3D if you want to do x, y, z. So that's your velocity vector. So the x component call it u, x component, the y component call it v, and then the z component call it w, not omega. Omega usually used for like that for angular velocity. Now, you know the definition of velocity, for example, u is the change in the x coordinate over t. Right? Delta t. dx dt is what? Velocity. That was the definition. Now, if you solve this equation for dt, what do you get? dt is equal to dx over u. And time is a invariant. It's something is unique. It's the same in all coordinates, x, y, z. It's not different. So if you go to y coordinate, what do you get? V velocity is dy over dt. If you solve for dt, what do you get? dt is equal to dy over v. And by the same token, if you solve for z, you get w is equal to dz over dt. If you solve for dt, you get dt is equal to dz over w. Because these are all dt, you can do this. You can say this is equal to dt, so this is equal to dx over u is equal to dy over v is equal to dz over omega. We call this equations of streamlines. I'm going to give a question in the midterm exam, the first midterm exam, from this. It's streamlines. So what are the streamlines? Mathematically, if I give you the velocity field, u, v, w, in terms of x, y, z, if you solve this is an ordinary differential equation. If you solve this equation, how do you solve it? You integrate both sides, right? If you solve this equation, you find a relation between a bunch of lines. You find some expression. And those lines are the lines that are passing through the velocity field. So if I make a tangent line to this bunch of vectors, you see that? We call this entire line, this single line, we call it the streamline. So streamlines are along the velocity field. So this is one streamline, and this is another streamline, and this is another streamline. We call it the streamline. Now, as you can see, a streamline does not depend on a single thing. Okay? It does not depend on a single thing. It's just a field parameter. You solve that, you get a streamline for the entire thing. Now, another definition they use, they say the straight line. So you see that's what, just what I said here.
We can integrate. It's a small piece of reddish dye.
Now, let's say you have something in the flow like this object, and the flow is going
After
along.
a small time, delta t has passed. The red dye marker has traveled away from its original location, and a small piece of blue dye.
Look at this location. If you consider this location, the fluid particles are going through this location, not one particle, not two particles, million, gazillion points going through this particle over time. Now, if I focus just in one particle, just like unlike the last problem I did not focus on one point, I'll focus on the entire thing. But if I just focus on one particle and I consider the particles that are mass passing through that point, we call that streak lines. So streak lines are the particles that are passing through just one single point over time. Okay? And then the next one is the pass line, which is the
from location.
pass off.
Past dye marker has
You see the path of those particles, we call it path line.
Streamlines.
So it's just the basic definition. We don't have time right now to watch the entire video, so I just want to show you, when you go home, please watch this video. These videos are very important. It's just not for fun. These are very important educational videos. Another important educational video is Eulerian versus Lagrangian. So let me make this short.
Laboratory point.
If you follow a particle in the field, so let's say there is a particle here, and I follow it, just like a person. I follow the entire history of what he's doing in the field. That's called the Lagrangian approach. As you can see in dynamics, vector statics, all we did was Lagrangian approach. For example, we did the system, we had 5 steps, right? The system was like the block, the object, the link, right? The joint in the truss. And we followed that. In the static, it was not moving, but in dynamics, we followed the block like a sliding down the incline, right? That's called Lagrangian. Lagrangian mechanic is you follow your system, right? Follow the system, called Lagrangian mechanic. But it still is 5 steps, nothing else. Now another approach is called Eulerian mechanic, and you, instead of following
To display the whole motion, and in more complicated situations, we avoid interference counter on the left.
Instead
That is, for
of
the
following the particle, you can say, you know what, the entire field, I can choose in the 5-step system, I can choose my system, just the volume enclosing this fluid. Now, here is the problem. This fluid is not always in that volume, because fluid is what? Moving. So there are always coming, some fluid coming in, and some fluid leaving out, right? Then it may be compressible. That means when the fluid is coming in, it may be compressed and temporarily some fluid stay there and nothing leaving, right? So I cannot hold it like that forever, right? Because the density is not infinite. You cannot put infinite particle in enclosure. So at some point you have to move. So this analysis, that instead of following a particle in fluid, instead of doing that, just consider the volume, people coming, people come up, right? This is called Eulerian. So Lagrange was the guy who was following the particle. Euler was the guy who said, stay here, choose a volume, and monitor which one is coming in, which one is coming out. So these are 2 approaches in mechanics. It's not fluid mechanics, it's general. This can be solid mechanic, electromagnetic. This approach that you track the particle is called Lagrangian. The approach that you don't track the particle and you choose the volume, right, called Eulerian. So this is another thing. Next video. Non-Newtonian fluids. Now we got some videos here. If you see, I said between the viscosity and velocity, if the relation is linear, right, that means the dV dy, this is, let's say y, is linear, then that's Newtonian. And we said mu is equal to, sorry, tau is equal to mu dy. So let's say this is shear and this is velocity. The slope of line was constant line. This is Newtonian. But if you go to a lab and use different fluids like honey, ketchup, right, you don't get that line. So if you put, just like in that device that you created, the cylinder, if you put other fluid there and try to compute the shear stress versus velocity, you get things like this. You get curve like this. You get curve like that. Obviously, these curves are sub-Newtonian. This is Newtonian. This is Newtonian. These are sub-Newtonian. These are super Newtonian. But both of them, sub-Newtonian, super Newtonian, they call them non-Newtonian. And all they do, they just make your integration. You see how beautiful it was with it? We use easy integration to find the relation between torque and viscosity. That was very easy. These guys, they make the mathematics really nasty. And before invention of computer, some of them were not even manageable. They could not solve it. The only way they could do it is to do experiment. There were no equation. But nowadays with the computer, so for example, one of them, I can show you, see, this is Newtonian, sub-Newtonian, super Newtonian. So you see this guy is like toothpaste. It takes some time to spread. So the shear field is a little bit resistant, this one. Right? So next we go. Hydrostatics, that's what we're going to do next class, chapter 2. We have to try it sooner or later, we have to teach you. And then the last concept of laminar versus torus flow. Look at this. You may get surprised to see that.
Personal injury case is like a jigsaw. Some pieces fall into place.
Okay. You see that? Look at it. It's just kind of like, it doesn't make sense. You see, you never see fluid like that. It's like picture. But in fact, it's moving. This is called laminar fluid. The particles of fluid, they move like laminates, right? They're just like laminates. They roll on top of each other. They don't mix. This is called laminar flow. And in real life, the laminar flow is almost non-existence because of something called vortex stretching. You will see that in graduates. But
I survived that one.
This is the dominant flow. You see that?
Well, here we are, half an hour, and
So the
one
velocity
drive
is
later.
coming here, and this is the plot. And you see, it's going to go over that. And the funny thing is, this is not experiment. This is numerical computation.
To pull the
This is not experiment. It looks so real, but it's not real. It's numerical.
entry tube further back, if that makes sense, further away from the nozzle outlet.
And this is also
And
simulation.
the further I pulled it away, that's just a little wing cap.
This is also another example. Look at that. This is the beam. This is the beam of airplane. The cross section is moving. Okay, yes, yes. You see, if you cut it, if you section here, you see that's the section, if you look it from the side, one dimension, then in this class, we are going to develop this equation called Navier-Stokes equation, but we're not going to solve it just like this. This is the next class, right? In this class, we solve simple one. This one, each guy solves the same equation, but with a lot of computational, a lot of different computational techniques. You see, if you zoom over it, this is the velocity. It's totally, you see all the particles are colliding each other, or mixing. And I can show you that even gets crazy. See, this is a big, call it baking. So if you look at it from distance, just like it does. So 100 years ago, because they didn't have computers to do all those things, everything like this was done in the lab, and nobody believed that this could be done like this. But right now, this numerical simulation, they do this thing they call high fidelity simulation. I mean, it's very high resolution. And the result you get, if you go to lab, you're matching it 0.00001%. 50 years ago, 20% was accepted. Right now, we're making it to 0.0001%. For example, on here, and you can do what
Arms
this is
and
just
angle
this is
degrees.
experiment. It's
1.
not even
Intake. 2.
This
Compression.
is actually
3.
an experiment.
Swirl,
You see,
which
there's
helps
different
maintain optimal
visualization
engine
techniques
efficiency.
to visualize inside the engine.
Focusing on the spark region and one cycle to the next, we see that the jet can impinge on the spark at different times.